Hello everyone. This is lecture 1 of course PE 500 Introduction to Differential Equations for Bioengineers. In this lecture we will cover the concept of calculus, including differentiation and integration, and why it's important in biology, and then how to deal with that in programming languages such as Python and MATLAB. So let's start. What is calculus? Calculus is a branch of mathematics, and it's divided into two main branches: differentiation and integration. Differentiation focuses on finding the rate of a change of one quantity with respect to another, while integration focuses on summing smaller changes to compute a total. These tools allows us to model and analyze processes that evolve over time. For instance, if you are studying the spread of a virus, differentiation helps you calculate how quickly the number of infected individuals is increasing at any given moment. On the other hand, integration allows us to compute the total number of people infected over a specific period. In biology, calculus is used to model and analyze processes that evolve over time. For example, in enzyme kinetics, calculus helps us understand how reaction rates depend on substrate concentration. Similarly, in pharmacokinetics, calculus enables us to predict how much of a drug remains in the bloodstream after a certain point or a certain period. By learning these mathematical tools, you will gain the ability to describe and predict biological phenomena with precision. So let's start with differentiation. The derivative of a function f of x, for example x squared, at a point x is the rate of a change of f of x with respect to x. And the definition of this derivative is rooted in the concept of limits, which captures the idea of a change as it becomes very small. To understand that, let's assume we have a point named x, and we got another point at the distance of h between x and x plus h. And as we mentioned, we have a function f of x. So we will substitute x and x plus h to the function and get the corresponding y values. Now we have 2 points. If we find the slope of or between these 2 points, which is delta y by delta x, which is the y value of this point minus the y value of this point, which is the numerator, over the difference in x values between x plus h and x, which is the numerator, we will gain this function, which is called the difference quotient. If we got this function and applied it to a limit where the difference or the change between x and x plus h is very small, let's assume it tends to 0, which is considered a very small value, this will be the differentiation or the derivative of the function f of x. In that case, if the difference between x and x plus h is very small, this means that the change or the slope of secant tends to be a tangent of the point. As you are going to decrease the h value, this point will move in that direction until it comes closer to the point x. So this will be called the slope of tangent line of the point x. So mathematically, we assume that h tends to 0, which is a very, very small value. And by that, it will be the slope of tangent line. So in the first equation, it represents the process of calculating the slope of secant line between 2 points of the curve f of x. And then, as we mentioned, it shrinks the distance h, which is the second equation here, between these points until it approaches 0. When h is extremely small, as we mentioned, h tends to 0, the secant line becomes the tangent line, and the slope of the tangent line gives the rate of a change of the function at that specific point. Let's apply the concept that we mentioned on x squared. So let's apply the definition of a derivative to a simple function x squared. Simply find the difference quotient and then apply it to the limit. So f of x plus h is x plus h squared. Substitute in that function, minus f of x, which is x squared, over h. Simplify. So x plus h squared will be x squared plus h squared plus 2xh minus x squared over h. This will cancel each other. So it will be h squared plus 2xh over h. Take h as a common. from here and here, it will be h plus 2x over h. This will cancel each other, so the result will be h plus 2x. Apply that to the limit where h tends to 0. So limit of h tends to 0 of the function or the equation h plus 2x, this will be 0. Then the result will be 2 multiplied by x or 2x. So the derivative of x squared is 2x, and in that case, the result will tell us that the slope of the tangent line to the curve y equals x squared at any point of x is 2x. And as you see here, there is no effect of the value h, as it's a very small value. Now let's understand the geometric and physical interpretation behind derivatives. The geometric interpretation of derivatives is crucial for visualizing how functions behave. When you calculate the derivative of a function at a specific point, you are essentially finding the slope of the tangent line to the curve at that point. The tangent line provides a linear approximation of a function near the point, making it easier to analyze complex behaviors. For example, in biology, tangent lines can be used to approximate the growth rate of a population or the rate of a chemical reaction at a particular moment. The local approximation is particularly useful when dealing with nonlinear systems, where exact solutions may be difficult to obtain. By understanding the geometric interpretation of derivatives, you can better visualize and interpret the behavior of dynamic systems. In physics, derivatives are used to describe motion. Velocity is a derivative of position with respect to time, and acceleration is a derivative of velocity with respect to time. These concepts can be applied to biological systems. For instance, the growth rate of a bacterial population is a derivative of the population size with respect to time, and the decay rate of a radioactive substance is a derivative of the remaining quantity with respect to time. Understanding the physical interpretation of derivatives helps bridge the gap between mathematics and real-world applications. For example, in enzyme kinetics, the derivative of the reaction velocity with respect to substrate concentration provides insights into the sensitivity of the reaction to changes in substrate levels. This interpretation is critical for optimizing enzymatic reactions in industrial and biological settings. There are multiple rules that can help you to differentiate correctly. The first is called power rule, and it's one of the simplest and most frequently used differentiation rules. It states that if you have a function x to the power of n, where n is any real number, for example 3, minus 2, minus 7, 0.5, and so on, simply the derivative of it is n multiplied to x power of n minus 1. So simply multiply by the value of n and subtract the value of n by 1 to be n minus 1. To understand it, let's apply these two examples. If you have x to the power of 3, then simply multiply that by 3 and decrease 3 from 1, then it will be 2. So the result will be 3x to the power of 2. And if you have x to the power of negative 2, then the derivative will be minus 2x minus 2 minus 1, then it will be minus 3. This rule is also helpful in biology when you are dealing with polynomial functions such as modeling bacterial growth. For instance, if you have a population size of bacteria which is modeled by this equation, for example, and you need to calculate the instantaneous growth rate of the bacteria, then you can get the derivative of this function. It will be 4 multiplied to t to the power of 3. So if you applied for the derivative a specific time period, then it will give you a quick and instantaneous growth rate at that point or at that time. It also applies to fractional exponents such as the square root of x, which is x over 0.5. Then to get the derivative, as we mentioned, take 0.5 here, which is 1 over 2 or 0.5 multiplied by x to the power of 0.5 minus 1, it will be negative 0.5. So with any real number, you can get the derivative. Another rule is called product rule, and this is applied when you are differentiating a function that is a product of two similar functions. Simply, f of x equals u of x multiplied v of x. So the derivative will be the differentiation of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. So at each time, differentiate one of these two equations or two functions and sum all of that together. So assume we have a function f of x squared multiplied by the exponent of x. Then the first function x squared, the derivative of it will be 2x multiplied by the second function plus the first function multiplied by the derivative of the second function. The derivative of e over x is also e over x. And simply, you don't have to memorize all of these derivatives. For example, the derivative of x over n or e of x or log x and so on. There are many tables on the internet that can help you to get the derivative of this simpler function. If you reflect that in biology, the product rule here is often used when you are modeling interactions between different variables. For instance, in enzyme kinetics, the reaction velocity might depend on the product of substrate concentration and enzyme activity. So, by applying the product rule, you can determine how changes in each variable affect the overall reaction rate. And if you are dealing with pharmacokinetics, the rate of a change in drug absorption may depend on the product of drug concentration and the blood flow rate. And here, the product rule will allow you to compute the derivative of the absorption rate with respect to the time. So simply, if you have two or more variables, the product rule will help you understand the rate of a change with respect to a variable such as time. The third rule is called Quotient Rule. And here, if you have or differentiating a function that is expressed as a fraction, like here, u of x over v of x, then simply the differentiation will be simply square the denominator, and in the numerator, it will be similar to the product rule here, but instead of plus, it will be minus. So apply here the product rule, the derivative of the first function or the function in the numerator multiplied by the second one minus the first function multiplied by the derivative of the second function. So if you reflect that on f of x equals to x squared over x plus 1, simply square the denominator, and here it will be the derivative of x squared, which is 2x, multiplied by v of x, which is x plus 1, minus the function x squared, multiply the derivative of x plus 1, which is 1. Simplify, 2 of x multiplied by x, it will be 2x squared, 2x multiplied by 1, it will be 2x, minus x squared multiplied by 1, it will be x squared, 2x squared minus x squared, it will be x squared, plus 2 of x, which is here, divided by x plus 1 squared. Again, to avoid memorizing the derivative of x, the derivative of x plus 1, x squared, and so on, you can get the help of differentiation tables from the internet. There are many PDF files or documents or web pages that can provide you the different tables for differentiation, and simply find the differentiation of x squared or x cubic and so on, and then write it. But you need to understand how to apply the different rules such as product rule and quotient rule and so on. To reflect that in biology, the quotient rule is particularly relevant for analyzing systems when you have a quantity that depends on the ratio of two others. For example, for the Michaelis-Menten equation, it describes the reaction velocity as a function of substrate concentration. V equals to V max multiplied by concentration of S over Km plus the concentration of S. And this equation is a counterstone of enzyme kinetics and provides a mathematical framework for analyzing reaction rates in biological systems, where V denotes the reaction velocity, which is the rate at which the enzyme converts substrate into product. V max represents the maximum reaction velocity achievable when the enzyme is saturated with substrate, while the concentration S is the substrate concentration, and Km reflects the substrate concentration at which the reaction velocity is half of V max, and it's a constant that serves as a measure of the enzyme's affinity for the substrate, where lower Km values reflects higher affinity and vice versa. So simply to understand the velocity changes or how the reaction velocity changes with respect to substrate concentration, you can apply the quotient rule to that equation. You will find V dash, or the derivative of V, will be like that. By simply finding this derivative and substituting with a point, you will get the reaction velocity at that point. The fourth rule is called chain rule. And this rule is used when you are differentiating composite functions. Composite functions means where you have a function is nested into another, or you have an inner function encapsulated by an outer function. For example, f of x is g of h of x. So this is the inner function and this is the outer function. The derivative of that function will be the derivative of the outer function multiplied by the derivative of the inner function. So if you have three nested functions, simply apply the derivative of the outer, multiply the derivative of the inner, multiplied of the derivative of any other inner functions. So if you have x squared plus 1, all of that to the power of 3, simply apply the derivative of the whole function. So this 3, move it here using the power rule. So it will be 3 multiplied that block or that function to the power of 2. Then move to each inner function and apply the derivative of it. So it's x squared plus 1, apply the derivative of it, it will be 2x. Multiply all of that together, you will get 2x multiplied by 3, it will be 6s multiplied by x squared plus 1, all of that over 2. To reflect that in biology, the chain rule is essential when you are going to analyze systems with one quantity that depends on another. For example, in bacterial population, it may depend on a temperature, and the temperature itself varies with time. So you have a population that depends on temperature, and temperature depends on time. So you have two cascaded or two composite functions. Let's reflect that mathematically. Let P of t represents the population as a function of temperature T, and T is a function of time, or the temperature is a function of time. So the chain rule will allow us to compute the rate of a change with respect to the time. So the population with respect to the time will be, apply the derivative of the first function here, will be the derivative of the population over the derivative of temperature, multiplied by the second function, which will be dt, or the derivative of time, temperature over the time. So again, moving from outside to inside, apply the derivative of each function and multiply all of that together. As I mentioned, there are many documents over the internet that contains tables like that one in front of you that provides you the direct derivatives or common derivatives. For example, the derivative of x is 1, the derivative of any constants is 0, the derivative of the power rule or the power rule multiplied by a certain constant, the trigonometric functions, the exponential and logarithmic functions, and so on. For example, we dealt of e to the power of x, which has a derivative of the same function e to the power of x. So you can use these tables or similar tables to help you find the instantaneous or the direct derivative of the common function. However, you need to understand carefully how to deal with the product rule, quotient rule, and the chain rule to be able to solve complex or composite functions. Now let's get some application of differentiation in biology. We will go through 4 applications: bacterial growth rate, product absorption and elimination, population dynamics, modeling tumor growth in cancer biology. Bacterial growth rate. It's often modeled using the exponential function because bacteria reproduce through binary fission, which leads to a doubling of the population at regular intervals. So the general form of the bacterial growth rate equation is PO, which is the initial population size, multiplied by e to the power of k multiplied by t, and k here is a constant or the growth constant. When it's positive, it's called growth, and when it's negative, it's called decay. So this is increasing and this is decreasing. E is the base of the natural logarithm, and P of t is the population size at a specific time t. To get the instantaneous growth rate of the bacterial population at any given or a specific time t, simply find the derivative of that function. So this constant will remain as it is. E of k multiplied by t has a derivative of e of k multiplied by t multiplied by the derivative of the inner function, which is k multiplied by t. The derivative of kt is k is a constant, so the final derivative will be k multiplied by po multiplied by e over kt. So if you have an initial bacteria of 100 and k, the constant, is 0.2 per hour and the time is 5 hours, then to find the current bacteria, you can substitute in the normal equation. But if you need to find the rate of change or the instantaneous growth rate, you will apply as derivative of that function. So simply substitute with these values in the original equation, you will get 271 bacteria at 5 hours with initial 100 bacteria. And the growth rate at the time will be around 54 bacteria per hour. So this tells you at 5 hours, the bacteria population is growing at a rate of approximately 54 bacteria per hour. So by getting that number, you can say after 7 hours, I will get that value by multiplying 54 by 7 or 7.5 or 8 hours and so on. So you will get the instantaneous bacterial population at that specific time. The second example is drug absorption and elimination, and the derivative here are used to describe the rate at which drugs are absorbed into or eliminated from the bloodstream. There is a common model for drug elimination, which is exponential decay function CO multiplied by e to the power of negative kt. It looks like the bacterial growth rate, but instead of getting a positive k, we have a negative k. As we mentioned, positive k for growth and a negative k for decay. And C naught is the initial drug concentration, and k is the elimination rate constant in this function. So the derivative will look like the derivative of the bacterial growth, but instead of k will be negative k, instead of p naught will be C naught, and that derivative is the rate at which the drug concentration is decreasing at a specific given time. So if you have C naught equals to 100, k equals to 0.1 per hour, and you have 5 hours, then at 5 hours, by substituting in the original equation, the concentration in the bloodstream will be around 60. And the rate of change at 5 hours will be negative 6 per hour. And this means at that time, which is 5 hours, the drug concentration is decreasing at a rate of approximately 6 per hour. So if you need the drug in the bloodstream to remain at a specific constant or at specific value, so you can use that formula or that model to optimize the dosing schedules so you can minimize any side effects or remain the effect of the drug in the bloodstream, especially if you are doing surgery and so on. The third example is population dynamics. And here we are going to study how populations of organisms change over time. And this is beneficial if you are going to study ecological systems, managing natural resources, and predicting the spread of diseases. There is a common model in population dynamics, which is the logistic growth rate, which can be described in this function. The growth rate, which depends on exponential growth and environmental constraints. Here in this function, P is the population size, T is the time, R is the growth rate, which means how quickly the population grows when resources are abundant. K is the carrying capacity, which is the maximum sustainable population size that the environment can sustain. And this derivative represents the rate of change of the population size at any given time t. To understand this equation, let's assume this example. We have a population of rabbits with the following parameters. The initial population is 50 rabbits. The intrinsic growth rate R equals to 0.4 per year, and the carrying capacity, which is the maximum capacity, is 500. So at the beginning of the experiment, or at time t equals to 0, the population is small relative to the carrying capacity. So if you applied that in the original equation, you will find that the growth rate is very high. But after several years, let's assume 20 years, for example, the population may reach of around 300 rabbits. So at that point, if you substituted in the same equation, you will get, or you will find that you will gain 48 rabbits per year. So from this number to this numbers in around 20 years or 25 years, the growth rate is increasing. It will increase until a certain point and then will decrease again because you have a maximum carrying capacity. So when you are going to approach the carrying capacity, which is 500, you will find that the growth rate will decrease. So this equation will let you understand that the growth rate increases at the beginning of the experiment and then decreases again when you are going to reach the carrying capacity. And this reflects the impact of limited resources such as food, water, and space. The fourth example is modeling tumor growth in cancer biology. And cancer biology here is a field where population dynamics and differentiation plays a crucial role in understanding the tumor growth and design the different treatment strategies. So if you are going to analyze the derivative of the different models for tumor growth, we can predict tumor progression and evaluate the effectiveness of different treatments. One of these models for the tumor growth or modeling the tumor growth is the Gompertz growth equation, which describes the tumor change over time or the size of the tumor, how it changes over the time. It's this equation, which is the growth rate constant multiplied by the tumor volume at time t multiplied by the natural logarithm of v over k. Again, v is the tumor volume at a time t, k is the carrying capacity, which is the maximum size the tumor can reach due to spatial or resource limitation. So this equation has two key features of tumor growth. It has an initial rapid growth when the tumor is small compared to the carrying capacity, so the growth rate is high, and we reflected that from the rabbits experiment. And it also has slowing growth as tumor approaches the carrying capacity. So when V approaches K, which is the carrying capacity, this term will decrease and this will lead to slower growth rate. So based on these two features, this will allow us or researchers or medical staff to predict treatment outcomes, optimize drug doses, and understand resistance mechanisms of the tumor or the cancer. To reflect that mathematically, let's assume we have a tumor or initial tumor volume of 1 centimeter cubic and a growth rate of 0.2 per day and a carrying capacity of 10 centimeter cubic. So at t equals 0, the tumor is very small and the carrying capacity is larger enough, so the growth rate will be high, around 0.46 centimeter cubic per day. And after several days, let's assume we reach it 5 centimeter cubic, the growth rate will be 0.69 centimeter cubic per day. So from here to here, the growth rate increases, but at the end, when you are approaching the carrying capacity K, which is equals to 10, the growth rate will decrease. So we have an increase or rapid growth rate and then decreases by approaching the carrying capacity. From that, we can update the equation to assume that the patient got a chemotherapy, which is D, which reflects the rate of tumor shrinkages caused by a certain drug. So there's the increase, there's a decrease by the drug or the chemotherapy. So by solving this equation numerically or using any programming language, we can estimate whether the treatment will stabilize or reduce the tumor. So by understanding or dealing with these applications, such as bacterial growth or modeling the tumor growth or the dynamic of the population, we can understand the meaning of differentiation in these cases. So differentiation is not just some equations or mathematical equations, but it's engaged into different applications in our real-world life. Now let's move to integration. Integration is the process of summing small pieces to compute a total. For example, if you know the rate for which a drug is absorbed into the bloodstream, integration will allow you to calculate the total amount absorbed over a specific time period. This is particularly useful where understanding the drug absorption and elimination is critical for determining the dosing schedules. The fundamental theorem of calculus connects differentiation and integration, showing that they are inverse operations. So the integral of a function f of x, it's the area under the curve of f of x between 2 points a and b. So if you have a certain function like that one, so the integral here between points a and b will be the area under that curve. And how to get that area? Simply similar what we dealt with differentiation with small h values. Simply here sum all of these values together to get the area under the curve. There's a symbol of integral, and a and b are the 2 points, the starting point, the ending point, and there's a function. By mastering integration, you can solve a wide range of problems involving accumulation, from calculating areas and volumes to modeling biological processes. Let's reflect that using geometric and physical interpretation. The geometric interpretation of integrals is central to understanding their applications. The definite integral represents the area between the curve and the x-axis. This area can be positive or negative depending on whether the curve lies above or below the x-axis. In biology, the area under the curve often represents a total quantity accumulated over time. For example, in pharmacokinetics, the area under the curve of a drug's concentration time profile gives the total amount of drug absorbed into the bloodstream. Similarly, in ecology, the area under the curve of a population growth rate function gives the total population growth over time. The physical interpretation of integrals is closely tied to the concept of accumulation. For example, if you know the rate of a change at which a drug is absorbed into the bloodstream, integrating this rate over time, this will give you the total amount of drug absorbed. Similarly, if you know the rate of population growth, integrating this rate over the time, it will give you the total population growth. In biology, integrals are used to model processes that involve accumulation. For instance, in enzyme kinetics, the total amount of product formed over time can be calculated by integrating the reaction velocity. This approach is widely used in biochemistry to study enzymatic reactions and optimize industrial processes. So let's go through the different rules of integration. The first rule is called power rule. Similar to differentiation, we got the power, multiplied it by x of n, and then decreased the power. Here is the opposite. Simply increment the power, and instead of multiplication, perform the division. So increment the power and divide over n plus 1. And n here is any real number except minus 1. Because if you applied minus 1 here, it will be minus 1 plus 1 will equal 0. And here, minus 1 plus 1 will equal 0. So it will be 1 over 0, which is not defined. And the integral here produces a constant c. It is called the constant of integration. So let's assume we have x to the power of 3. The integration of it is done by increasing the power and dividing to the new power. So it will be x to the power of 4 divided by 4 plus the constant. Again, for x to the power of negative 2, increment the power, it will negative 2 plus 1, it will be minus 1 divided by the new power, which is minus 1. So this will result in negative 1 over x plus c. In biology, the power rule is often used to calculate the total quantities over time, as we mentioned in the interpretation. So if the rate of bacterial growth is modeled as this equation, the total population growth over the time can be computed using the power rule and integration. Simply, to calculate the total, integrate this equation. So the integration of this equation will be t to the power of 3 over 3. Then, to get the values, substitute by the top value minus the lower value. So after getting the integration here, substitute by t, it will be e to the power of 3 over 3 minus the substitution of 0 in this equation. So 0 over 3 here will be 0. So the final result will be t to the power of 3 over 3. And this reflects the total bacterial population growth from time t0 to t equals to t capital. So let's assume t capital is equals to 3. So the total bacterial growth will be at that time will be 9. By substituting in this equation, 3 multiplied by 3 multiplied by 3 over 3, this will get 9. The second rule is called substitution method, and this is a very powerful tool or technique for simplifying integrals by introducing a new variable into the equation. And it's helpful if you are dealing with a composite function. So how to deal with it? Simply substitute or rewrite in terms of a simpler value, for example u, then perform the integration and substitute back to the original variable. So let's assume we have a function e to the power of 2x and we need to integrate that function. Simply substitute by 2x by the variable u, which is simpler. So this will be done by replacing all of the x values by u values. So it will be the integration of e to the power of u, and we need to replace also the derivative of x here. So simply apply the derivative of this equation. U will convert by du, 2x will be converted to 2 of dx. So dx here will be du over 2 by simply getting that value here. So the new equation will be 0.5 multiplied by the integration of e to the power of u dot du. And we move the constant here outside the integration because you can do that with any constant. So if you have any constant multiplied by the equation here, you can extract and get it outside the integration. But this cannot be applied to addition and subtraction. This only can be applied to multiplication and division. The integration of e to the power of u is also e to the power of u, and the same of differentiation of e to the power of u is e to the power of u. So the integration of this value will be e to the power of u multiplied by 0.5 plus c, which is the constant. Now substitute back using u equals to 2x. This will be 0.5 multiplied by e to the power 2 of x plus c, which is the constant. Let's reflect that in biology. If you need to get the total drug absorbed over time in the bloodstream, you can use simply that model or the model in hand and integrate it. So if we need to integrate that function, which is a function over another function, which is composite, simply replace that function with a simpler value called u, for example, and continue the integration process, and then substitute back to get the original variables. And in that case, you will get a specific or a certain equation, and this equation in that case will reflect the total drug absorbed or the total value or the area under the curve between 2 points. The third rule is called integration by parts, and it's essential for integrating products of functions that cannot be solved using simple techniques like substitution. And this equation is derived from the product rule of differentiation. So if you have products of two functions, for example u and v, which are differentiable functions, the integration of them will be u multiplied by v minus the integration of v dot du. And du and dv are the corresponding derivatives of u and v. Let's apply that on that example. To select which is u and which function is v, simply let u to be the simpler function, and dv is the other function that can be easily to be integrated. So in that case, let's pick u to be x and dv to be e to the power of x. So when we differentiate u to be du, it will be 1 dx. So it's a simple function to differentiate. And the same here. dv, we need v, so we will integrate e to the power of x. It will be the same e to the power of x. Now we have u, v, du, and dv. Substitute in the equation, which is here, u multiplied by v. We have u x and v e to the power of x. So it will be x multiplied by e to the power of x minus v du. V here is e to the power of x, and du is 1 dx, which is the integration of e to the power of x dot dx. The integration here is simple. It will be e to the power of x like that, plus c, which is a constant. By taking the exponential as a common factor, it will be x minus 1 by the end, plus c, which is the constant. So now we dealt with integration and differentiation. We got the meaning behind that and the different rules, and how that can be integrated and reflected in biology applications, such as modeling the cancer spread or getting the total of the drug absorption in the bloodstream and so on. And from that, we can understand that differentiation is the rate of a change or the instantaneous rate of a change at a specific point, while integration is the accumulation of a specific variable or multiple variables in a specified period, for example, from A to B. So if you need to get a certain value or a certain rate of a change at a specific point, apply differentiation. And if you need the total value of that variable, apply integration. Now let's move to handling calculus using Python and MATLAB. The exercise here will allow you to apply calculus concepts using computational tools, which are Python and MATLAB. And these tools are widely used in scientific research and industry, making them valuable skills for your future career. In Python, there are multiple packages such as SymPy, NumPy, and Matplotlib that will allow you to symbolically differentiate and integrate functions and also help you visualize the results. In MATLAB, functions like def and integral provide efficient ways to perform numerical differentiation and integration. So let's start by the first example about differentiation. Let's assume we have that function, which is x to the power of 3 plus 2 multiplied by x squared minus 5x plus 1, and we need to familiarize and know how to use Python and MATLAB to apply differentiation to that function and visualize both of them. So by the end, we can get a visual figure or a visualization of f of x and f bar of x or f dash of x, which is the differentiation of f of x. So in the code provided to you, you will find two folders, MATLAB and Python. In each of them, you will find the different scripts for the language that you need to use. Here the different scripts for Python and here for MATLAB. In the differentiation example for Python, you will find that example. It's called lecture 1, lab exercise 1, differentiation, and the same for the other one and so on. So in any lecture, you will find that the notation followed here is the name of the lecture and the name of the exercise and a simple keyword about the meaning of that exercise. And the same for MATLAB. In Python, you usually import the different packages after installing it on your computer. So we are using NumPy for numerical operations, Matplotlib for creating plots and visualization, SymPy for symbolic mathematics. We have the function that we defined in the presentation. So to make it a symbolic equation, we need to use the function symbols and define the name of the variable that will be used and store it in a variable called x. Then define the function, apply differentiation of the function with respect to x using the function def, and then you can print both of them. So if you executed the code, it will print the function and the derivative of it, as you see here, the function and the derivative is 3x squared plus 4x minus 5, which is the correct derivative of it. Then we need to apply visualization or visualize both of the functions so we can get the following figure. So simply define the x-axis. Here we defined 500 points between -5 to 5, and this function will create an array or a vector of 500 evenly spaced values between -5 and 5. Then we need to convert back the symbolic functions to numerical functions. We can substitute into them using lambdify function defined in this package. We will define x, which is a symbol variable, f, which is a function, and numpy is the package here to convert the symbolic to the numerical format from this package. Now we have the numeric function. Apply the different x values. We will get the corresponding y values for that function. Do the same for the derivative. You will get the corresponding y value for that derivative. Then, using matplotlib library here to plot and save the figure. Here we define the figure. We plotted the f of x. Then we plotted f dash of x, which is the derivative. This is in orange, this is in blue. Then we defined a title and labels for x and y axis. We added a grid and the legend to the curves. Then we saved the figure and displayed it in front of you. When you execute the code, it will display something like that, which is the plot with f and the derivative of f in front of you from -5 to 5. So simply here, if you have another function, you can set it here instead of the predefined function. For example, let's assume we have y multiplied by x to the power of 5 minus, and we need to determine the derivative of it and plot the corresponding derivative and function. Simply, as you noted, change the variable f and execute the code. You can also change the start and ending points and the number of evenly spaced points. It will show a plot like that for f of x and the derivative of f. Now let's move to MATLAB. You will find the different scripts for MATLAB. As we mentioned with Python, the same is here for MATLAB in the MATLAB folder. You will do the same operation, define the symbolic variable using sims function and define the variable after it, define the function, apply the derivative, then you can print the different functions, that function and the corresponding derivative, and also you can use the linspace to create 500 evenly spaced between the points -5 to 5, and to convert from symbolic to a numerical function, you can use the built-in function called MATLAB function, and then substitute to get the corresponding y values, then create the figure, plot the first, which is the function f of x in red, and the derivative of it in blue, set a title, x label, y label, and display the legend. And we use hold on and hold off if you are going to plot multiple figures or plots. So after the first plot, set hold on, so you can continue designing your plot. And after you complete that, release the plot using hold off. When you execute the code, you will find the function and the corresponding derivative. It will also display the plot like that, f of x and the corresponding derivative from -5 to 5. So by plotting f of x and the derivative of it, you can get some insights on how the slope of the curve changes as x varies. So in that case, for f of x, or the derivative of f of x, you will find that it decreases until it reaches a certain point, and then it increases back again. And you can say that we got a local minima or maxima. A local minima, where you find the lowest value, is called local minima. And if you got something like that, this is called local maxima. And if you have a curve or a derivative like that one, you have a minima here and another minima here. So if you have multiple minimum values, so the lowest value, which is here, this can be considered as a global minima, and other lower variables can be considered as local minima. The same for maximum values. If you have multiple maximum values, so the maximum point will be global maximum, while others will be local maxima. So if you are dealing with an example that tries to find the global maxima or local maxima, and the same for local minima or global minima, you can apply the derivative and then set the derivative to 0 and solve the equation mathematically or numerically and find the x values that achieves that point. Let's move to another example about integration. So we need to compute the integration of that function or that composite function from x equals 0 to x equals 1 using Python and MATLAB. And then visualize that and visualize the area under the curve, which is the concept of integration. So we need to report a figure like that from 0 to 1, and this is our curve, and this is the area under the curve. So if you go to the second example, you will find a similar pattern to the previous code, but here we used the quad function from SciPy package, which is responsible for the integration from between certain points. So we defined a function here, the exponential of minus x to the power of 2, applied the function to f from 0 to 1, and got the result. This is accumulated result or the total computed integral value. So if we executed the code, we will get around 0.75, which is the total integration value from 0 to 1 to that function. And the rest of the code visualizes the area under the curve. So here we created 500 points, got the corresponding values, created a figure, and used the function fill between to create the area under the curve between x values and y values. Then we plotted reference lines, horizontal and vertical, at y equals 0, x equals 0, x equals 1. So it can visualize the boundary area. So from the visualization, we can understand it's like a box. Then we added title, labels, grid, and legend. Finally saved and displayed the figure. So it looks like that from 0 to 1. These are the vertical lines and the horizontal line. This is the curve in blue and the area under the curve in light blue. If we did the same with MATLAB, we will define the symbolic x, define the function, apply the integral using the integral function to calculate the definite integral between 0 and 1, created x and y values, created the figure using the reference lines, added different properties such as title, labels, grid, and legend, and released the plot hold because we have multiple plots in the same plot. If we executed the code, we will get the same value here, which is around 0.75, and this is the corresponding plot. These are the reference points, 0 and 1, and the reference lines. This is our curve. This is the area under the curve, which reflects the integral from 0 to 1. So if we calculated all this area, this is reflected by the integral value, which is about 0.75. So in this lecture, we defined the concept of calculus, including differentiation and integration. We went through different rules for differentiation and integration, such as substitution and power rule, chain rule, and so on. Then we reflected that on some biology applications, such as bacterial growth and the cause of drugs in the bloodstream, and how we can model different applications to understand when it increases or decreases. And finally, we went through two examples using MATLAB and Python for differentiation and integration. We understood the meaning of local and global maxima and minima for differentiation and the area under the curve for integration.